Let me admit something that may sound slightly illegal for a PhD candidate. When I see a new equation in an AI paper, I do not immediately try to solve it. I usually read the sentence before it, then the sentence after it, and then I ask, what is this thing trying to make the model do? Because sometimes an equation look like somebody dropped an alphabet on the keyboard, but the actual idea is surprisingly normal. Choose something, compare something, punish one mistake more than another, give more attention to one piece of information, use more computing power when the problem becomes difficult. That is usually where I begin, not with can I derive this, but with what behavior is hiding inside this. Last week, we built a map for an AI paper, Mission, Move, Proof, Build. This map tells you why you are inside the paper and roughly where you need to go. Then you arrive at the technical section and the author suddenly decide English was becoming too comfortable. Now there are Greek letters, subscripts, brackets inside other brackets, and one symbol that was apparently defined 3 pages ago while you were still emotionally stable. This is normally where confidence disappears, but the equation is not a separate universe. It is the part of the same story. We just need to translate it. So I'm Hamza. I work in AI research and build real AI systems. And this is Paper Fearless. One paper, one clear idea, one buildable move. Today we are making the mathematics behave like normal language again. Let us start with something many people have heard about, DeepSeek. DeepSeek version 3 is a huge model, yeah? It has hundreds of billions of parameters, but for each token, it does not active the entire model. Only a smaller part becomes active. This is called mixture of experts systems. In short, MOE, maybe you have heard. The name sounds dramatic, but imagine a large company. Someone arrives with a legal question. You do not call engineering, design, marketing, finance, HR, and the person responsible for ordering coffee. You call the relevant people. That is the basic intuition. Different parts of the model acts like specialists, and routing mechanism decides which specialist should handle each piece of information. Now, inside the paper, that routing decision may appear as scores, probabilities, normalization, top case selection, and several equations. But before touching any of that, ask, what is the equation's job? Its job is to decide which expert should work on this input. That one sentence already gives us somewhere to stand. Then ask what goes into the equation. Usually, the model has produced some scores. One expert looks very suitable, another looks somewhat suitable, the other looks less relevant. Those scores go in. So what comes out? A decision about which expert receives the input, and sometimes how strongly each expert should influence the result. Now the symbols are beginning to behave like something. Yeah, a higher score means the expert probably matters more here. A lower score means maybe leave this one alone. So we still have not derived the equation, but we understand the decision it is making. A recent research preprint takes this idea one step further. It asks, why should every piece of input receives the same number of experts? Some inputs are easy, yeah, others are confusing. So think about planning dinner in WhatsApp group. Someone says pizza, fine. And then one person answers problem solved, but another person came with some more conditions like we need something halal, vegan, nut-free, under 15 euros and still open at midnight maybe. So now the entire group wakes up. One person checks the menu, another checks allergies, someone checks the price, someone else sends a restaurant that closed in 2019. The question became more uncertain, so it needed more help. The research idea is similar. When the model is confident about which expert should handle a token, it may use fewer experts. When the routing scores are spread out and the model appears uncertain, it can involve more experts. Now imagine seeing the entropy equations for that. You could begin by trying to remember logarithms, or you could first translate the behavior. Why does this equation exist? To estimate how uncertain the routing decision is, what goes in the model scores for the available experts, what comes out, a measure of uncertainty, what happens when uncertainty rises, right? And then the system can activate more experts, and what behavior does that create? So simple input receives less computation, more difficult or ambiguous inputs receive more help. That is the story inside the equation. Do I completely understand every mathematical detail now? No, but do I understand what the equation changes inside the system? Yes, probably. And that is a real layer of understanding. It gives me a reason to study the deeper mathematical terms on that. Without that context, I am just moving symbols because the paper told me to. Here is another example. Let's say, think about the face unlock from your phone. Yeah, it can make at least two very different mistakes. It can look at you and say, "No, you are not you." Annoying, right? Or it can look someone else and say, "Yes, this is definitely Hamza." So much bigger problem. Both are errors, but they do not have the same consequences. So while training a system, the researcher may decide that one kind of error should receive a stronger penalty than another. Inside the paper, you may see two loss terms and a weight, often something like alpha or lambda, controlling their importance. Again, do not begin with the symbol. Begin with the decision. The equation is asking, how much should the model care about the mistakes compared with that one? Now imagine alpha increases. So what changes? That part of the loss becomes louder. So it pushes the model more strongly. Alpha is basically a volume control. The symbol itself is not the interesting part. The interesting part is what becomes louder when you turn it up. Yeah. So this is the question I use most often when reading equations. If this value increases, what does the model do differently? That question works surprisingly well. If attention weight increases, which information receives more attention? If a loss weight increases, which mistakes matters more? If a threshold increases, does the system become stricter or more permissive? If uncertainty increases, does the model slow down, ask for more help, or activate more experts, or become less confident? A variable becomes understandable when you can describe the consequences of moving it. And this matters because this equation do not stay in papers. Eventually they become the behavior. A loss function can influence which error a medical model tries hardest to avoid. A threshold can decide whether a security system accepts or rejects someone. A routing function can decide how much computing power an AI system uses. A similarity equation can influence which people, images, or situations the model treats as related. The mathematical choice may be hidden, the behavior will not be. Yeah. So as a researcher or builder, I do not only ask what does this symbol mean, I also ask what kind of system will this symbol help to create. You can also use ChatGPT, Gemini, or other AI tool to help translate the equation, but please do not only paste a giant equation and write explain. So that is how you receive a beautiful new wall of text to replace the original wall of text. So ask maybe smaller question like, what is the purpose of this equation in the method? What goes in and what comes out? What happens when alpha increases? What behavior is this loss encouraging? Explain this as a decision the model is making. And one of my favorite questions, give me a real life analogy, then tell me where the analogy stops being accurate. That final part matters. An analogy helps you enter the idea. It should not quietly replace the actual mathematics. Then go back to the paper, check the definition of every variable, read the lines and after the equation. Read the lines before and after the equation. Look at the experiment that tests the behavior you think the equation creates. If the author claim their uncertainty mechanism activates more expert for difficult inputs, do their experiment actually show that? If one loss term is supposed to improve safely, which result demonstrates the improvement? Yeah. The translation gives you a hypothesis about the equation. The evidence tells you whether your translation is correct. So when you reach the next frightening equation, do not fight the whole thing at once. Just have a conversation with it. Why are you here? What do you receive? What do you produce? What changes when this value moves? And what does the model do differently because of you? So purpose, input, output, change, behavior. Then connect it back to the mission of the paper. That is enough for your first pass. Later, when the equation becomes important for your research or your project, go deeper. Study the derivation, learn the mathematical concept, reproduce it in code. But now you know why you are doing that work. So after this video, choose one equation from any AI paper. You do not need to explain the whole equation. Just complete these sentences maybe. So this equation helps the model ... and then maybe add it receives what it receives ... then it produces, and when this value increase, the model what it does ... So answer these things. That is your translation. So write the behavior in the comments. You can leave the Greek alphabet inside the paper. At this point, we have opened the door, we have built the map, and now the technical language is starting to make sense. But there is still one problem. A paper may contain 20 equations, 5 modules, 3 training tricks, and enough acronyms to start a small government department. So you can understand all of them and still miss the one idea that actually makes the paper important. So next week we answer how do you find the central idea hidden inside an AI paper. That is the next step in becoming paper fearless.